Our first talk today is by Tom Scanlon of UC Berkeley, and the title's Parameter Identifiability Through Canonical Bases.
Okay, so thanks for the invitation. Those of you who invited me to speak. I'm going to be talking today, as you see the title is Parameter Identifiability Through Canonical Bases. Before I get into the details, I should just say a little bit about the genesis of this project. So as you might note here, I'm thanking the NSF for funding us. This is part of a focused research group that we have with Alexey and Anand and various other people associated with it, so Remy and Mikhail. Gleb was part of it for a while. To try to connect ideas from model theory to differential algebra and then to applications. And when I say applications, I mean applications inside of the sciences. I think when this idea was first proposed to Anand, maybe we thought it was a little bit crazy. To take these ideas coming out of one of the most abstract parts of mathematics, mathematical logic, and to hope that it would say something about mathematical biology, well, that can't possibly happen. Except that it did. And so that's exactly what I'm going to be describing. I'm going to be describing my take on this project, which is more so from the point of view of logic, more so from the point of view of model theory. Although the work that's mainly Gleb and Alexey have been doing on this brings it back to computations, and maybe one day you'll hear them explain what's happening at the computational side. All right, so the problem that we're going to look at is a very general kind of problem. Consider systems of equations, and here Gleb pointed out to me that I have been calling these input-output models, but these are actually state space systems or state space models. It's just basically a system of ordinary differential equations. So that's the first part. The bold is supposed to indicate it's a vector of a variable. So the first derivative of x is given by some function of x and two other variables. I'll tell you what those other variables are, the mu and the u. We have an output function. So this is y is given by some function of x, mu and u. And we might have a constraint, although my more applied co-authors think that we shouldn't have a constraint, and so that's going to go right, very quickly. So in this picture, we refer to x as the state variables. It's supposed to be describing the basic state of whatever your system happens to be, whether it's the pressures or the velocities or whatever of the system that you're describing. U is usually referred to as the input variables, which perhaps the experimenter has control over. What you actually get to observe are the outputs, the y, although very quickly I'm going to take y equals x, so that you're allowed to observe everything. But in principle, maybe it's only possible to observe some fraction of the system, and that's going to be what you see with the y. Mu is, at least in almost every application, taken to be a sequence of constants, and we call those the parameters of the system. And so in your model, you're going to have some big system of linear equations or nonlinear equations. That's the more interesting case for us today. With some numbers that you happen to throw in. If you've ever looked at what people in applied mathematics do, they just fit everything. Like just add numbers here and there, so that's whatever kind of equations they might have seem to fit whatever data that they have, and those are your parameters. And I suppose in principle, f, g, and h could be more or less any kind of functions, but for us to say anything, we're going to stick to polynomials. Okay, so we can work at the level of differential algebra. And as I mentioned before, even though I think that we should have a constraint, we're not going to. Okay, so the constraint equation is just going to disappear from the rest of what we discuss. Okay, so the basic problem that we're going to address is the parameter identifiability problem. Sometimes this goes into the name of systems identification, where we'd like to know, given the outputs, can you tell what the parameters were that went into the model? Now, why might this matter? Well, if you're trying to, if you know the general form that your model is supposed to take, and it has all of these undetermined coefficients and constants floating around, how do you determine which numbers to plug in there? And the first question you might ask before answering how do you figure out what numbers to plug in there is it even possible to figure out what numbers to plug in there? And one way to tell whether it's possible, to say that it's possible, is that I do some experiments, I look at the outputs, and can you, from those, somehow compute what the parameters were supposed to be? And this takes various forms. The methods that I'm describing today could be applied to many of these other forms, although I'm just going to focus on the parameter identifiability for purposes of exposition. But you might want to know, well, can you tell what the input was, given that you know what the outputs are? Remember, the input was actually a sequence of functions. It's a differential variable, and that's a more complicated thing. Maybe you want to know what the input was, given that you know the system. Maybe you even know the parameters. Could you recover, well, various things you might ask whether you could recover. All of these kinds of questions can be addressed with the kinds of things I'm talking about today, although for what we're actually going to work out, we're just going to focus on recovering the parameter. And more precisely, how am I going to mathematize this? I'm going to treat this as a problem in differential algebra. And what I'll mean by identifying the parameters is that you can find the parameters as a differential rational function of the output. Now, which output, which state variable? Well, again, to make this, to have a precise mathematical content, you look at a generic solution to the equation, and then you ask, for that generic solution, can you write the parameters, can you write mu as differential rational functions of y? And there are variants of this, whether you want to allow the input variable or not as part of your data in the output construction. The actual constructions we'll end up doing, we won't have any input variable, so that this distinction isn't going to matter. But you might ask, can you compute mu instead of the differential rational function generated by y, or maybe you want to allow the input also as something you're allowed in computing. So to say that the parameters are identifiable would mean that this differential field, now this is a differential field where mu is a sequence of constants, so the differential field generated by mu is just going to be the field generated by mu. To say that the parameters are identifiable would be to say that this differential field is just equal to q. And maybe a weaker thing that you might aim for, if you can't actually recover the parameters, is to determine, well, which parameters can you recover? How much can you recover about the parameters? And that would be the question of how, well, can you just compute what this field happens to be? If it's not everything, what is it? And so those rational functions of the basic parameters we'd call the identifiable parameters in the system, and we're looking to identify those. All right, so there are some obvious reasons why this might be impossible. Some really silly reasons why this might be impossible. And one silly reason why this might not be possible is maybe those parameters that you're considering don't even appear in the equations. Okay, just because I wrote it as x prime equals f of x comma mu, okay, so it doesn't mean that the variables that the mu variables actually appear in that function f. Okay, and if that were to happen, I guess there's some rare cases where it's such a stupid system that you could still recover the mu. But if you had any transcendental parameters, any transcendental components instead of the mu, you're just not going to find them. Totally impossible. All right? Okay, that's a stupid reason. But you could take the stupid reason and hide it. And one way you could hide the stupid reason is by having a system where really the coefficients are rational functions of the basic parameters of the mu. Okay? So here's just a silly example, although you can come up with much more complicated examples. My two parameters are mu1 and mu2, but they only enter the equation as a sum. Well, that's all the more you're going to be able to recover is the sum. There's no way you can recover mu1 or mu2 separately, but you could recover the sum. Okay? And so you've chosen the parameters poorly. Right? They really aren't the canonical parameters for the system. And so if you want to have any hope of recovering the parameters, it better be the case that the system that you're considering has what I'll call canonical parameters. All right? And so here's what I'll mean. This first approximation to what I mean by canonical parameters is that if you were to choose different parameters, a different sequence of numbers, you get an inequivalent system. Right? So there would be some solutions to one system and not the other, and vice versa. Okay? So you need to do that. Now, this notion of canonical parameter, as I said up there, is a very standard notion in many parts of mathematics, but in particular, we even use exactly this word in talking about canonical parameters for definable sets in mathematical logic. And I'll give this definition. I'll write down Greek symbols for formulas, but there will be no quantifiers. Well, actually, in line, there are some quantifiers there. Okay, so you have to do a little bit of logic. Okay, so here's the definition, what it means to be a canonical parameter, just in general. Okay, so you have some formula. So the formula might be the formula which defines my system of differential equations, and that's what we're going to apply this to. And I've broken the formula. The variables come in two kinds. I have x and y. Those are really tuples of variables. And I'm thinking about the second variable, y, as parameterizing a family of formulas, a family of definable sets. So you can vary the parameters in y and get different sets of solutions. And I'll say that this formula has canonical parameters if, when you vary the y, you get different sets. Right? So the formula with C is equivalent to the formula with D if and only if C equals D. And in that case, C would be the canonical parameter for the set that it defines. Now, it can happen that you have a formula, you have a nice system of differential equations, like I said, and it doesn't have canonical parameters. So there may be different choices which give you the same sets, but you might want to convert it to an equivalent system. And if you can always do that, if you can always convert to an equivalent system which has canonical parameters, then we say that your theory has elimination of imaginaries. So what are the imaginaries here? The imaginaries are the canonical parameters. Okay, so here's the formal definition, what it means to eliminate imaginaries. You start with your formula. In this case, I'm starting with C, which is bad for some reason. It doesn't have, you start with phi. Maybe it's bad. Okay, you did something stupid, like you did the thing with x prime equals x plus y1 plus y2. Okay, that's a poor choice of a formula to define that system because it doesn't have canonical parameters. So you look for a different one. Okay, and the different one, my C, would be x prime equals x plus z1. Right? That would be a good system. Right? And the reason why it's the correct system to use, or a correct system to use, is that it defines the same collection of definable sets, the same collection of systems, in the sense that every instance of phi is equivalent to an instance of C, and vice versa. And this is the formal way of saying that every instance, for every choice of a parameter for phi, you can find a parameter for C, so that the sets they define are the same. Okay. And likewise, the other way around. And C is good. So the example that I gave, where you started with x prime equals x plus y1 plus y2, you replace it with x prime equals x plus z1, that would be a good system. And what's useful for us here is that the theory of differentially closed fields of characteristic 0, which will be the background theory in which we'll do differential algebra, eliminates imaginaries. So it's always possible to convert some system of differential equations to another system of differential equations where the parameters for the second system are canonical. Maybe not in exactly the same form that I wrote on the first slide. And what I mean by that is that in the system on the first slide, they were given by actual equations, and you might have to allow inequalities to make this transition exactly work. But at the very least, if you're okay with constructible systems, it's always possible to convert to a different system where you have canonical parameters. And that being the case, I usually think of this as, okay, so thinking back now to what the computational question might be. Maybe the first step before you do some kind of, well, first or maybe after you realize it's not identifiable, maybe the step you should do for some system of, for one of the input-output equations is to check, is the system set up in such a way that you have canonical parameters? And if it's not, then compute the equivalent system where you do, and then ask the question about identifying the parameters for that equivalent system. So that's not what I'm going to be describing, but that's something that you really ought to do. Okay, so there's a more refined notion of canonical parameter coming out of model theory, and this is to say that the existence of this notion is what's made our entire FRG project happen. Okay, so when we noticed that there were these problems coming out of identifiability analysis that looked exactly like the kinds of problems that we do in more abstract model theory, having to do with the canonical base of a type, we saw that really there might be a tight mathematical connection between the two, and this is the concept which makes it work. Okay, so this is the canonical base of a type. I'm going to specialize the case that we actually care about, the differential fields, rather than to give some complete abstract nonsense definition of this. But it is important for the kind of developments that we do to know that there is some abstract theory behind all of this, which made it possible to develop the consequences that we have. I mean, everything can be translated back into differential algebra, and making the translation makes it possible to do computations after the fact. But knowing what translation to do requires thinking, at least for me, it requires thinking at the abstract level. All right, so I'll just remind you, notation that's, okay, so I do it just the ordinary Roman I instead of with the bold I, but in case the ideal of some tuple over a subdifferential field is just all the differential polynomials which vanish at that point. Okay, so let me define some notions. First, I'll define the notion of stationarity, which, in this context, to say that my tuple A is stationary over a given differential subfield just means that its ideal of differential polynomials which vanishes on it is absolutely prime. Absolutely prime means that it stays prime even after you pass the algebraic closure. As you might guess, because stationary and prime don't seem to be the same word, this is a word which comes from the more abstract kind of picture, but I'm going to stick to the word just so that you can match notions from one to the other. So it's basically just means that anything that you might want to determine about the locus of this tuple over K remains invariant as you pass to the algebraic closures. Now here's the definition of the canonical base. So the canonical base, my tuple A over a subfield K, is the differential field of definition of its ideal. Okay. So now you might ask, why does that exist? And you should ask why that exists. And it's a non-trivial fact that this exists. Right? But it does. Right? And it's a consequence of, you need to prove that ideals of definitions or fields of definition exist for ideals in algebraically closed fields, and you can reduce to that using elimination of imaginaries. I mean, there's a bit of work to be done here, but it exists. Right? So there's a smallest field of definition for the ideal. So you can find some system of generators. Well, I should say, yeah, you find some system of generators or isolating differential polynomials for this field or for this ideal over some subfield, and that will be sort of the smallest such place where you could find some such generators, in the sense that if you were to copy that field somewhere else, actually move the field, then you move the ideal. That the ideal actually changes. Okay, so how do you realize it? So there are a couple of ways that you might do it. We all start with the algebraic description. So algebraically, what you can do is you can find what's called the well. Okay, actually, it's better to take. Okay, it did say just. Did they say characteristic? Yeah, characteristic generating set. This is what I want to say. So you find a characteristic generating sets. You choose the polynomials in there to be monic, and then you look at the coefficients of those differential polynomials and the field that generates. That's going to do it. Okay, so algebraically, if you actually want to know how do you actually compute the thing, you look for characteristic generating sets, and you find the coefficients of the polynomials there. The differential field it generates. That's it. Maybe from a more model-theoretic logical point of view, what do? So, morally speaking, everything that you want to know about this tuple A over K is determined by a single formula. This is what Michael was asking for yesterday, although it doesn't really exist, although it almost does. Okay, so you can find a single system of differential equations satisfied by A, which almost isolates, right? No, that's actually has a technical notion. Which isolates the type up to lower dimension. So anything else which satisfies those equations will either have the same exactly the same ideal, or it will satisfy some equations of lower order. And so you find that formula which describes that, and the canonical parameter for that formula is going to do the trick. Well, one way you can compute that formula is by finding these characteristic generating sets and writing down saying, I satisfy these equations and nothing simpler.
Does characteristic generating set mean something different than characteristic set?
Yeah, it does.
It does.
Okay. And to be totally honest, I've forgotten the exact extra condition it requires, so I'm not going to repeat it. Maybe Alexey wants to say. Yeah, it's a bit too technical to. You have to say something about which variables appear as the leaders, which ones appear as the. So it's so it's a bit too technical. So it's definitely too technical for me to remember exactly what it says, and even if I did, it'd be too technical to repeat. Like I could pull it up on the screen and read it to you, and we still wouldn't have it. Okay. All right. So let's come back to the problem that we're dealing with, and I'm going to simplify it by forgetting the input variable is gone. We already got rid of the constraint equations. That's gone, and I'm also getting rid of the output equation. Well, I haven't really gotten rid of it, but I've just made it the trivial equation that y equals x. So the state is the output, and I'm just going to deal with this from this point on. That's right. Yeah. So it's not that we're unable to prove things about the other case. It's just I don't want to deal with all those extra complications right now. Okay. All right. So I'm going to write little k for the fields generated by these coefficients. And I'm going to assume for the moment that mu is a canonical parameter. Right, so we have some hope of recovering it. And so what does our identifiability problem come down to now? We want to compute the canonical base of this type, which we've said under our hypothesis that mu is a canonical parameter would be the field in question. We want to know, can we compute it just by knowing A? Can we write that? Can we write that field of definition just as a differential, in the differential field generated by A? Okay. All right. So I'm going to prove one proposition, and this is it. So the only proof that I'll go through today. And with this proposition, what we'll show is that if you're asking what is the canonical base of your tuple over the full field of constants. So I do the full field of constants, and I want to know, can I determine what equation, so how do I generate the ideal of that given tuple over all the constants? That you can compute by knowing just one solution. I know one solution to the equation. I can compute its canonical base over the full field of constants. just from that. All right, so there are, this is actually pretty close to the full proof, like that we have on the screen here. So I'm going to go through the whole proof of this. Okay. All right, so you have to do a little preparation ahead of time, just so that you can think in terms of automorphisms. But you can assume that the ambient differential field in which you're working is homogeneous enough so that you can do Galois theory. Right? So that is that fixed fields of closed subgroups corresponds to differential subfields, and exactly in the way that you would like in ordinary Galois theory. So in particular, you can arrange that the differential field generated by this tuple A is just the fixed field of the Galois group, or the field of the differential Galois group. Okay, I shouldn't say differential Galois group because I don't mean this Picard-Vessel group or anything. Field of the group of automorphisms of the differential field, which fixes that tuple. Okay. So arrange that. It's just the usual algebraic nonsense that you can arrange that your automorphisms, the fixed field of the automorphisms is exactly the differential field generated by the tuple. Now we make an observation. Make an observation that the constants are just defined by an equation x prime equals 0. So if x prime equals 0, then sigma of x prime equals 0. So the field of constants is fixed setwise by every automorphism of the big differential field, and in particular is fixed by the automorphisms which fix the tuple A. Right? Okay, that's maybe an obvious observation, but an interesting and useful observation. The next observation is that this ideal of differential polynomials which vanishes at A over C is also fixed by every such automorphism. So why is that? So if you take some differential polynomial which vanishes on A and has coefficients from C, you hit it with an automorphism, those coefficients are going to move. Okay? But f sigma of A sigma is the same as f of A sigma. Okay? So it's 0. So f sigma applied to A is still 0. And from our first observation, the coefficients stay inside of C, which means that new polynomial, which also vanishes, differential polynomial, which also vanishes on A, also has coefficients in C, so it's in this ideal. Okay, so what have we just said? We've said that this ideal is invariant as a set under all automorphisms which fix A. Okay, so now just by the general Galois theoretic nonsense, that means that the field of definition for it is contained in the fixed field of all of GA, meaning it's contained in the set of GA. And we also know that, of course, I could define the ideal of A over C. So whatever its field of definition is the subfield of C, so it's contained in the intersection between those two. Okay, so the canonical base is contained inside of here. And in fact, you get an exact equality. Well, you get exact equality. Maybe I won't go through that direction. Right? But you can just check that if you had something which was in this field but not in the canonical base, then something will go horribly wrong. Okay? So it either violates stationarity or it violates the independence, properties of independence the canonical base has. Okay. So if you're working over the full field of constants, you can compute the canonical base from one realization. Okay, so that looks hopeful. I mean, it looks like this general nonsense allows you to compute things.
How do you find the C?
What?
How do you find the C?
How would you find which C?
The big C, the constants.
How would you find them? What do you mean? It's the constants, the complex numbers. I mean, it's the field of constants, everything which vanishes, and where the derivative vanishes in your differential field.
Right, but this differential field, it has a solution of a differential equation. There could be some complicated constants in there.
Okay, well,
You don't know them in advance when you start with the system.
that's true. that's actually a big problem, and that's part of why why things fall apart later on. Yeah, you're right. So to make this work, you need to work in. Okay, so the argument is assuming it's working inside of a differentially closed fields. Okay, you don't have to quite go that far, but you do need to arrange that the differential fields that you get from whatever your original system was after joining A has the same field of constants that you had before, which may or may not be true because there may be new constants, and this canonical base may very well be defined using new differential rational functions of A, which give you constants. So yeah, that could certainly happen. Okay, so there's another technical proposition which I'm not going to go through the proof of, but I'll just point out. It tells you that if you're interested in computing the canonical base over some other field of constants, what you can do is you can do the first step of computing the canonical base of your system over the full field of constants. You get something, and again, it turns out these differential fields are finally generated, so you can find some tuple which generates it, some C. And then you compute the canonical base of this thing, of this tuple of constants, over the small field. And that two-step process will compute for you the canonical base of the original tuple over the base field. Now, morally, what goes into this? You're trying to determine what are the coefficients you need in order to describe the system over some small field. And, well, you can compute what happens over the full field of constants. And so you have some system equations defined over this new tuple, over the full field of constants. But this tuple, the C, of course, maybe is not actually defined over K. It satisfies it's in some algebraic variety. And so you basically just have to say, in order to describe the equations over this field, we just say, I look for something which, a generic thing which satisfies those equations that C satisfies over K, plug them into the equations that you would have had, the system you would have had using C, and then that gives you a way of describing the equations that would be satisfied over K. I mean, that's morally what goes into that kind of picture. Technically, it's just the algebraic argument. Okay. So the point of all of this is to say that the story doesn't work the way that the applied mathematicians wanted it to work. Okay? So it's not always possible to compute the canonical parameters from a single realization, even for very, very simple systems. And the reason why you might expect this is that thinking in this abstract way of the canonical basis, we just know from so many examples throughout model theory that it's extremely rare to be able to compute the canonical base from one realization. When it does happen, when you have a theory where you know that always happens, you can always compute the canonical base, then you can prove that the theory is rather degenerate. So it's either so degenerate there are no interesting relations going on, or maybe it comes from linear algebra in a precise sense. So if something comes out of linear algebra, then sure, if you know one point in a coset of a vector space, then, well, that tells you which, if you know which linear space you're translating, you know the space. But that's basically the only time when you can be guaranteed to be able to compute from one realization. A little argument here about algebraically closed fields, but I think I'll ignore that and just go to the example. Right? Okay, so I'm going to give you a construction. It's a very simple construction showing that it's not always possible to compute the canonical parameters from one realization. Okay? So I fixed 3 algebraically independent elements by constant fields. If you want, C is the complex number, so that makes you happy. Right? So we just take 3 algebraically independent numbers, B, C, and D. And I'm going to define a 4th number just by multiplying and adding. Right? So that's the most basic thing you can do in a ring. Right? So you can multiply and you can add. So let's do both those things and put together and make one more element. All right, so let's compute the canonical base of the pair B comma C over the other 2 parameters. over D and D. All right, so these are constants. Right, so the differential equations, okay, I said its ideal is generated by that. They also have x2 prime equals 0, x1 prime equals 0. And this one equation, which is monic, and so you can just tell that it's going to make it stationary, and you can compute what you see what the coefficients are. D and D, it's monic. It's going to generate the canonical base. So the canonical base of BC over DE is just the field generated by D and D. It's true the other way around, but it's not so important. One thing to note, because this field D generated by algebraically independent things, and the first three were algebraically independent transcendence degree 3, follows that you cannot get that field. You can't get K inside the field generated by B and C. Because if you did, you would have that this field would contain a transcendence degree 3 field, and it doesn't. It's transcendence degree 2. Okay, so you can't compute the canonical base just from one realization, but this is kind of silly. It's just this isn't necessarily even in the form of the right kind of equations that we're looking at. It's just with constants. But now I'm going to look at something which is a differential equation. Basically going to replace E with the derivative of A and D with A. Okay, so you look at a solution to this order 1 equation. It's not a very complicated equation. Right? It looks like an inhomogeneous linear equation, and it is, but I'm going to turn it into something which is not quite linear. And what I mean by turning it into it's not quite linear is I'm going to liberate B from this equation and treat that now also as a variable. And now I have a system in these two variables. So A is going to correspond to x1, and B is going to correspond to x2, which is satisfied by A comma B. And this is one of our basic systems. And this violates the canonical the parameter identification. So you cannot compute the canonical base of this. You cannot compute the parameters from a single realization of the system. Right. On the next page, I give a little argument, which I won't go through. You can read this later. Okay, so but I'll just say that it's comes from the computation that we did there, just using the linear equations in the field, and this reduction of computing canonical bases over the full field of constants. So basically, the point is that there are new constants that you need to consider that you haven't seen yet, that aren't already present, just knowing D and D. And the fact that you can't get your hands on those with just one realization is what makes it impossible to compute the parameters from one experiment. Okay, so there's a verification, which we'll skip. All right, well, that's bad, okay, because these mathematical models are supposed to allow us to live in this world. And if we can't actually tell what the coefficients of the models are by doing experiments, then how do we use the models? Well, we could do what people usually do, which is they don't really care that what they're doing is wrong, and they just make up numbers, and things more or less work until the planes crash. And but we're not going to let them do that. Okay, so we're going to give them a way to tell how to compute the parameters, and a way to do that is by doing more than one experiment. So if you do one experiment and try to compute the parameters just from that output, that might fail. But why not do more than one experiment? Right? So you have a system that's supposed to describe, you know, this model is supposed to describe infinite many possibilities. Well, you can do a few experiments to test what's happening in that model and whether the model actually fits your data. And so we're going to suggest that you do that. Okay, so we have a system again, and I'd like to to compute mu from the parameters from the output. Again, if we want to be able to do this, the parameters had better be canonical, but you know what that means. I gave you a general sense for that. If it is possible, well, we'd like to know, okay, I just said you can't always do it with one experiment. Can you do it with 2, 3? How many do you have to do? After which point you can do a computation to know you actually have the parameters. Or at least, can you compute a number so that if you can't solve the problem with that many experiments, it's impossible to solve the problem. And I'll just say that the bound that we end up computing will depend on how you think about this problem. So whether you treat the input variables as part of the system or not, whether they change or fixed, I'm going to kind of ignore those subtleties and mainly deal with the case where there are no input variables, but you're allowed to deal with the case with their input variables. And the answer is that this problem was solved in, the precise statement I'm going to write down is not written down in classification theory, but it was basically solved by Schiller 40, 50 years ago in the context of totally transcendental theories. And so here's the theorem, which says exactly that you can always compute the parameters from finitely many independent experiments. It doesn't look like that's what it says, but I'll explain why it says this. Okay, so I'll read this, and then we're going to translate this into a statement about differential equations. So we work in a totally transcendental theory. We have some tuple which is stationary over some base, B, which B is going to be our field K. Then you can find some number n. You can even, in some cases, even compute what the number is, so that the canonical base is definable over an independent sequence of realizations of the type of A over B. And I give a computation for how you might bound that number n. The number n can be bounded by 1 plus the Lascar rank if that's finite. Okay, so Dave knows what I'm talking about. That's probably it. So I'm going to, Oh, sorry. Yeah, but you're looking at your computer, so you weren't listening to what I was talking about. Because you already know what this means. Think, why do I have to look at it? Okay, so let me explain what it means. Okay, so when I say totally transcendental theory, for us that just means differential fields, or differentially closed fields. So differentially closed fields are totally transcendental. This is a theorem of Lenore Bloom from 1969. Independent here just means that, basically means that so I take my first one, A1, it should have the same ideal that A has over K. And then you go to A2, it should also satisfy the same equations that A satisfied over K, but nothing new over A1. So the ideal of definition of A2 over the field generated by K and A1 should still be the same. You go to A2. It should satisfy the same equations that A satisfied over K, but nothing new over the new things, and so on. Okay. Definable from just means in the differential field generated by for us. And Lascar rank, well, okay, I won't go into what that means, but in the case that we're considering with the parameters that are constants, it's just the transcendence degree. Okay. So what that theorem says is that it's always possible to compute the canonical parameters of a system from S plus 1 independent experiments, where S is the transcendence degree of your sequence of constants. So if you have mu1 up through mu s, you can compute those by doing S plus 1 experiments. Okay. All right, so this does have an algebraic counterpart, which can be implemented. And what I call the Schiller reflection principle is really just an abstraction of what might go under the name of Lagrange interpolation, or the method of undetermined coefficients. And if you think about it that way, then you can convert all of that reasoning back into linear algebra and actually compute what the canonical parameters are from a given independent sequence of solutions. Okay. So how do we do this? I'll just go through a little bit of a computation. That's just the outline of how the computation goes. So I'm going to just think about the one variable case just to make life a little easier on me to write, so I don't have to write so many different systems. So I'm trying to compute the minimal differential polynomial of some elements over maybe a field of constants. I want to know how many independent realizations do I need. Okay, so of course the differential field is basically generated by one differential polynomial. Basically meaning up to taking saturation by inverting it separate. Okay, so what do? Well, you write down what you want the polynomial to be, but you don't know what these constants are. And now you want to compute those. And so I compute those by turning this now into a linear problem in the constants. So if I were to plug in the element a into the variable x, I have to differentiate it, raise it to powers, and so on. But I can treat those as the coefficients. So I treat the values, the various monomials of the points that were, of our solution function, now as the coefficients of a linear equation. Well, if you have enough linear equations, you know the only solution that's, or maybe a one-dimensional space of solutions, you make it monic, you know the solution. So basic linear algebra, you have to check that things are independent and ranks and everything, but basic linear algebra is going to tell you you can compute what those coefficients are if you have enough solutions.
You use here the independence.
Oh yeah, you have to use the independence in order to guarantee that that's the rank is correct and that you get an invertible matrix if you do things. I mean, when I say basic linear algebra, I mean you actually have to do some linear algebra. You have to do some work, but it's the kind of work that we all know how to do. Okay, so you do some basic linear algebra, and you find that you can compute what the unique solution to the system is going to be, and more than S does it. Okay. Now you can improve these bounds sometimes by being a little bit more clever and thinking about the fact that the coefficients are constants, taking into account, say, what various Wronskian ranks are. I won't go into that, but this helps with the computation. All right, so what else might you see here in this multivariable case when you're doing computations? In the minivariable case, well, there's more you have to do because there are more polynomials you have to compute. And there you'd have to think about this more technical notion of the characters of presentation, which I'm not telling you precisely what the definition is, but it's not that complicated. I mean, it's just, you just have to do something a little bit more technical. You might also be able to speed the computation by working with maybe a different basis instead of monomials, although which basis you choose is not at all obvious. And so working with monomials is maybe the naive thing to do, and it always works. Although maybe not as quickly. If you have some other kind of situation, maybe you choose a different basis, and it'll be a bit faster. The upside of all that is that we know that you can always get it down to S+1, and with some computational tricks, maybe you can bring it down sometimes. But we have examples showing that that bound is in general sharp. So don't expect that cleverness is always going to help you. All right, so what kind of extensions might we have with this method? Maybe you want to deal with systems which involve partial differential equations. And the beautiful thing here is that the model theory is already developed. And so all of the basic theory that's needed to make this work is known. Although to actually implement it is a different story. And so one will have to think about how it's implemented in the computation scope. You might want to deal with difference equations or with differential equations. That should work, but the model theory is more complicated and it hasn't actually been developed. So knowing that the background theories aren't there means that there's more work to be done, but I would expect that this kind of extension ought to be possible. And with that, I'll thank you all, and thank you.
Questions for Tom?
I have a question. I'm not sure it makes sense, but one could ask the same questions for just polynomial equations.
Yes.
You know, the reduced minimal Grubner bases give you the field of definition. Is what you're doing something that's known already in that context?
I think yes. I mean, so yeah. You can,
I mean,
of
from
course.
a model theoretic point of view.
Okay, yeah. So I guess the point is that from the model theoretic point of view, like all these questions to me are known.
The same.
Are they all the same? Or they're all known? But you mean like what is how many parameters or how many experiments do you need? And I don't know to what extent that's been computed, but yeah, it should be. I mean, so the general bound that I gave already is, you have worst cases for algebraic equations where you need the full s+1 experiments to find the parameters. But then you ask if you specialize to some monomial equations, you know the dimensions, and you know something about some kind of Newton polytope or something. Can you bring that down? I'm sure you can, but I haven't really thought about the computational issues. I mean, is there something that you've thought about?
But if you do polynomial equations, you have to make sure it's an absolutely reducible thing. For differential equations,
Yeah, sure,
it's kind of easy to make it meaningful because it's always like, well, if you do x prime equals f of x, something is always absolutely reducible. For polynomial equations, maybe there are many things. It's hidden under the constraint.
Yeah, but you can decide whether it's
Yeah.
reducible.
Yeah.
Assuming it is.
And one more thing to add to this, I think, is that so that gave an upper bound, but one can actually find out what that number is by an efficient algorithm, fast algorithm. Maybe that is off by one at most. So it's not just an upper bound, but actually you can get an actual number quickly.
That really is.
That's what. Yeah. So enough for the number of experiments to conduct.
So how can, in practice, how can biologists know they've done independent experiments?
Yeah,
Or is it, or
you can only know that probabilistically. That would be probabilistic. Yeah, so in practice, you don't actually know that there isn't some extra equation which is satisfied. So yeah, that'd be probabilistic.
But mathematically, you just you copy the same equation, but put a new variable into it. So you had x prime equals f of x. You do x prime equals f of x, and y prime equals f of y.
Right, but
You keep the same parameters. That's what you do mathematically.
yeah, so I mean, well, but okay, so you add the new variable, you can find the differential rational function, and okay, I suppose I suppose maybe the answer is that you could tell that you've done it's independent enough if that differential rational function is defined. Okay, so after the fact, after you actually compute what our bound is, compute with the differential rational function which computes the canonical parameters, you just find you need to avoid a certain indeterminacy locus. So as long as your experiments don't satisfy those equations, then you're okay.
Is there a reasonable algorithm for starting with a system of equations and getting a system that has canonical parameters?
I don't know what you mean by reasonable, but
Not search.
no. I mean, so it is okay. Yeah. So, okay. I guess the answer is yes.